Evening, everybody. We'll be with you in another 2 minutes. Some other things that I need to load onto the computer, just load them. All right, evening, everybody.
Yes, sir.
Yeah. Um, we want to talk about some things before we go back to talking about control. So, um, let's begin with um, writing state space equation. Oh, who recorded?
Give me the permissions, you know.
Yeah. All right. So, we're going to be doing things by hand for a little while. So let us say that you have a transfer function. Well, let me start from the yeah, we have a transfer function 2s plus 1 over s squared plus 4s plus 3, for example. Um, and we want to write the state space equation for it. We won't be going back through the thing about writing the state space equation for a differential equation to learn the signals. But what we want to do is just be able to look at this and write down the state space equation. So it's an S square. So that's the second order system. So that means that is a 2 by 2 matrix. So we're going to have 2 and we're writing this assuming that x1 is our, well, x1 gives us our y or some form of our y, and x1 dot gives us x2 in some kind of way. So when we're writing this, we would write 0 and 1 as a standard, and for the denominator, we have 4 for the s and 3 for the we would write -3 and -4. If we were multiplying these out, this would be -3x1 -4x2. x2 represents the derivative of x1. So the first derivative always goes with my x2, and the one that has no derivative always goes with my x1. That is how I remember it. 0, 1 is standard. And same thing again. So my output section, or my Y for my output is going to be 2S. So I said the S represents the first derivative. So we're going to reverse the order again, 1 and 2, because remember now, 1 is going to go with the first derivative, and 2 is going to go. 1 is going to go with the output, 2 is going to go with the derivative of the output. So, in other words, what I'm trying to say is this one is the S. X2 represents the derivative, which we call in the S. So that is how I remember to write them down. We're not so keen on writing it down.
Saying about the 3 out of the denominator, like a 2, right? Yeah.
Which part?
Yeah, it just come back.
Oh. All right. We're not so much worried about it in this strip here. MATLAB still loading back, so I don't know if anybody is tuned into MATLAB. I won't be able to use MATLAB for a while. It was at 5%. So
I mean, you're just installing it, sir?
I don't know what happened to the computer. And in the middle of installing it, the computer locked down. And then, you know that blue screen that you get where it's saying something went wrong?
Yeah.
And lock off. Well, that's what happened after that. The second time, in the middle of it. So I don't know. Anyhow, so we are going to, if we are using MATLAB, what we are going to ask you to do is the Y is going to represent the denominator, the coefficients of the functions in the denominator. So the coefficients of your Y in your denominator are 1, 4, and 3. And the coefficient of your X in your denominator is going to put 0, 2, and 1. And so you're going to write G is equal to transfer function XY. And it will write it will supposed to write our equation as is here. So I don't know who have access to MATLAB. I'll give make you do the screen.
Yeah, write it in, sir.
Can you share screen now?
Yeah, so allow that no security. Allow participants to share screen. Yeah. Oh. All right. So share the screen.
It's we cannot share it while somebody else is okay.
Yeah, so 0 to 1. Teach a high school picnic. Let's see if what them do we can do too. Right on the screen. Nope. right. So that is going to write, like I said, it's going to write it back as a transfer function for you. So now, if you want to write it in state space, your square bracket to type it. Not k equal to just square bracket. A, B, C, D, A, comma, B, comma, C, comma, D, comma. Sorry, take out the comma for the D. Square bracket, close, equal. Transfer function, TF, TF. Just TF. When you finish it, TF to T2, the number 2, SS, state space. Open bracket, that one. X, Y, X, comma, Y. And press enter. All right. So you see, it has written the A, B, C. D is always 0 if the transfer function is not is one that is usable. If you get a value for D, then that transfer function is not a realizable transfer function. So it writes it for you, but notice that it's upside down, back to front. So it is x2, x1. The bracket is x2, x1. Right? So it's not x1, x2 like you will see on the textbook, right? It's not x1, x2, it's x2, x1. It's upside down. So you see everything is back to front. And when you do the transfer function to state space for MATLAB. All right, so it's TF transfer function to state space. And you have it there. All right, so you're able to write the transfer function as in terms of state space easily. So now, if you are writing it with the x1, x2, just bear in mind that it is upside down. It is x2, then x1, not x1, then x2. All right. That is their software, and you can tell them how to write their thing. So that is just it. Like I said, every textbook will have it x1, then x2, but they have it the other way around. Now, there are some things that we need to be able to find. So, for example, is this system stable? Then we'd have to find the roots of the characteristic equation. So, so just type in like z equal roots. That was y.
Yo, scroll up your screen a little bit for please.
And there's some MATLAB have it, you know.
That's alright.
Yeah, close the bracket with the y, and so that is z equal roots y. So you will get the roots of the characteristic equation there, or any equation. So it will tell you -3, -1, right? Or if you want the roots of the characteristic equation are the same thing as the eigenvalues of the matrix. So EIG of the matrix that you have common A. Supposed to give you the same 3, negative 3, negative 1. All right, so the roots of the characteristic equation and the eigenvalues of the matrix. And then you can look at that and say, what comment on the stability of the system and so forth and so on. So you can determine the stability. All right, you can just I'll go back the screen a little bit. We need to talk about two other concepts before we go back. All right, so we need to talk about controllability. And observability. So let me put the definition. A system is controllable, and that is any system. Any system at all, an economic system, electrical, mechanical, chemical, biological, and a biological system might mean the child that you had, the girlfriend or the boyfriend. I don't know if any girls in the class. So any system at all is controllable if and only if there exists, and that is the back way E means there exists. Get used to it.
Sir, you say there's no one in that class?
Me say if there, I don't know if any. That's why I say girlfriend or boyfriend.
Alright, sir.
So it's controllable. If there's an input, which we're going to call X, that causes the output Y to go from its present value to a desired value in a finite time t. All right, so let us say that this is your system and this is your present, and you want to get to over here, and so there must be an input U all right, so the present X and Y. It doesn't matter how well. Yeah, it doesn't matter as long as the time is finite. So you can't wait forever. So let me terrorize Zavina and say, let us say that the present state is girlfriend and the desired state is wife. Then the system is controllable. If you can, there's an input U that will take you from that state to the desired state. If there's no input, or if the input cannot take you there in a finite time, it's taking forever, then what we are saying is that system is controllable. So the finite is important. Alright, so the finite is important. This finite means unmeasurable. So finite also means measurable. So this definition controls talk about any system. So it is controllable. If and only if we have something some input we can carry us from the present state to the desired state in a finite time. So if we can't find any input to carry us from, there's nothing that we can do to carry us to the desired behavior, then that system is uncontrollable. And if we can, if the input will get us there, but it's going to take not a measurable time. It's going to take till infinity for it to reach there. Then it don't make sense either, because the whole of ever dead same way. So by the time it reaches, so we still define it as uncontrollable. So that is the technical definition of something that is controllable. So mathematically, we can determine that if we know the parameters of the system, we know the system matrix and all those type of things. So we can determine mathematically if a system is controllable. So what we'll do is form the matrix. And this is how the matrix, I'm going to call the matrix X. So it's going to be B, A squared B, A to the n minus 1 times B. Is full rank. So of course, when I was in maths class, nobody ever explained to me what that means. A matrix with full rank. So let me, and so let me explain the rank of a matrix, and then explain the easy way to sort out this, and then we can look at 1 and 2 examples. So rough work aside, let us say I have this simultaneous equation. So this is my equation 1, and this is my equation 2. What can you say about these two equations?
One is half the other one.
One is half of the other one. So I multiply equation 1 by 2, and I get equation 2. So basically, it's only one equation that we have here. It's not two. They might try to disguise themselves as two equations because you see me write down 2 equations, but it's really one equation. The 2 of them is the same thing. So here is it. There's only one equation that we have here. So the rank of this set of equations is equal to 1. So if we have a 2 by 2 matrix, then to solve it, we need 2 different equations. So a 2 by 2 sorry, we have two set of variables, x and y. We need two equations to solve it. And that would mean if we have two different equations to solve it, then the rank is 2. So full rank means that the number of variables I have is the number of different equations that I have. So we can solve that. So we can solve that equation. Now, what that I will wait until you're doing your masters in control to get into all of that. But bear in mind that we have said that B is your input matrix. And we said that you must be able to find an input that way to take your system, which is A, from point X to point Y. So it must mean that when I take that system and put it together, I must be able to get a solution. So one of the things that we are looking at is that when you take the matrix and the system and put them together, we must be able to solve that equation because we are going to be looking for some x's and y's that will carry us to the point. Sorry, we're going to be still looking for a u that will carry us from point A to point B. The output that we want, y, is dependent on x1 and x2. So the system must be able to be solved. All right, like I said, I'll leave it for the when you're doing your master's and PhD, control for them to go further. All I'm saying is that what we mean by full rank is that your system must be able, you must be able to solve the system. So the easy way to know if we can solve the system is that if you look at this set of equation, there's no one value that we're going to solve it. This has several solutions. So this is not a solvable system, but then what we can look at is the fact that the determinant which is 3 times 8 minus 6 times 4. 24 minus 24 is 0. So we can easily say that our system here is controllable if the matrix. So we can say the system is controllable if the determinant of x is not equal to 0. If the determinant is equal to 0, we can solve the system. So that is one way of determining it. Of course, so let us look at the example that we have here. The example that we are, let's do an example. Let me do an example. So we want to find out if this system is controllable. So now, so we're going to form the matrix X, which is, well, let's write down first of all, what is A and what is B. So A is 0, 1, 2, 4, and B is the input matrix, which is 1, 2. So our matrix X is equal to B and then AB. It's a 2 by 2 matrix, so we're stopping at the second iteration. So if you know, if it's a 3 by 3 matrix, then we would stop at the third iteration. That would be A, B, A squared B, and so forth and so on. So we can determine when to stop by the size of the system. So what we have up here is that we say we go B, A, B, A squared B down to A to the n minus 1B, because if it's a 10 by 10 matrix, then we need to have 10 terms inside that expression bracket here. All right. So our X is equal to B and then AB. So that is going to be X is equal to, like I said, I'm doing it by hand. So this is 1, 2, and then it's going to be 0, 1, 2, 4 times 1, 2 is equal to 1, 2. And if I multiply this matrix, that's 0 times 1 is 1 plus 1 times 2. You hear me just say 0 times 1 is 1. All right. So let's try that again. 0 times 1 is 0 plus 1 times 2 is 2. So that's 2. And then 2 times 1, 2 times 2.
In.
10. Yeah.
Yeah.
I just realized I said 2 times 1 and 2 times 2. It's 2 times 1 and 4 times 2.
Yeah, 10.
Which is 10. And the determinant of X is going to be equal to 1 times 10 minus 2 times 6. That's not 0. So therefore, this system is observable. All right. So what we are saying now is that whenever we're sorting out any system, when we're working out whether a system, any system at all, once we get the transfer function, one of the first things that we must find out is if it is controllable. All right? Came to you this year, but we would emphasize it in previous years. So if you go in the exam and you're asked to solve a system, you don't just jump and solve it, find out if it is controllable first. Because you will work and not get an answer. And you wonder, what we do wrong? We never multiply this right, we never do this. Some systems are not controllable. Just like some people. Just like Some, well, people are systems, can be viewed as systems. Some systems are just not controllable.
Sir, the
Right?
statement, should that be observable or controllable?
Or controllable. When I reach observable yet.
Sir, our next question, sir. It says 0 times 1 is 1.
Is 0.
So 2, you're right, back 1. Yeah.
Well, 1 times.
No man, you 1 and the 2 depend that the side there before.
This 1 and 2 here.
Yeah, you can just write them back.
Oh, okay.
Oh, should I put a bracket around this? Right? So system is controllable. So we can find an input to control the system to carry to the desired output. So all the things that you see I was doing before with the pole placement, we just need to be cognizant of the fact that going forward, whenever we have a system, we have to check if it is controllable, if there exists a solution for the system that we are talking about. All right, and if because if the system is not controllable, then we are going to be in a position where, like I said, we're going to be working towards a result, and we can reach it. And there are many systems that are not controllable. But most of the times we can use common sense and look and see that the system is not controllable. If I might get into politics, or not so much politics, but if you're going from the earth to the moon, so your present state is earth, and your desired state is moon. Can you find the input, which is the amount of gas or fuel that you need to take you from here to there? And how are you going to get that fuel? You're going to need some form of propulsion, and you're going to need something to take you from here to there. And if you do your calculations, you will see maybe that something not right in the calculations. When I say something not right in the calculations, people have said that the moon landing is fake. The Americans were just trying to make sure so them outdo the Russians. So them stage this thing so they land on the moon and all of those type of things. But you can calculate and find out that but this thing is not. This thing requires an input where we cannot come up with at this present moment in time. But anyway, let's leave that alone. The times we are in, we need to be careful what we are talking about. Uncle Sam is listening. And others. All right. So let me stop share, and so we're going to take another system. So we're going to take another system and we are going to find out if that system is controllable, but we're going to use MATLAB and do it. So ask Mr. Campbell to go back on MATLAB. And so we're going to type in the matrix A, which is 0, 1, 0, semicolon. Oh, put space between them for me. And then the 0, 0, 1. And then it is minus 2, minus 3, minus 5. I can't close the bracket. So that is A. B now. What was B? Maybe
B a 112.
B is 1, 1, 2. But you have to put the out on the outside of the bracket. You have to put a transpose, which is a not the comma, the for the one quote name, apostrophe. Or put the apostrophe at the end of that. All right, maybe still. All right, and then now, so we're going to say x is equal to quote bracket b and then space.
Are that the bracket there, sir?
Yeah, same one. Space AB, A star B, space A squared star B, close the bracket. And then find the determinant, DT x minus 226. So that's not 0. So it is not, it is controllable. Alright. So I don't remember the command. CNT. Type in help controllable.
What that, sir?
Help controllable.
Oh.
Bisa type in command tab na. Wala na extra.
I want LR2L.
A 12 in a controllable. I think. All right. Everybody, all right. Give me everybody, let me just talk about observable, and then I'll give you the command, because you never have to do all of that we do. You could just type in the command for controllable. And then from there, you could take it. Yeah, my MATLAB is at 34%. All right, so I was looking at the command for controllable. CTRB. So go back and go back to CTRB, open bracket, A, comma B, and close the bracket. Okay, so I thought it was going to give you the determinant of the matrix. All right, now, so one other thing now. So type in rank, RANK, of the answer that you get. So rank answer. Supposed to get 3. All right. So rank supposed to give you 3. So if you type in rank and you can, instead of typing in determinant, you can also type in the rank of the matrix, and the rank is a 3 by 3 matrix, so the rank supposed to be 3. That is full rank. So therefore, you have 3 distinct equations, so you can solve it for x1, x2, and x3. So you can also do that. Especially when you have a big matrix working with. I've seen people working with 200 by 200. Sorry, 201 by 201 matrix. So you don't really want to go do B, A squared, B, A, and so forth, going down the line. So you just write controllable A, B, and then find the rank of that matrix. All right. So if you have a controllability, you can either put it out as we have it, or use the commands that we have here. All right. So let's go back and talk about observability. So a system is observable if the states So a system is observable if the states of the system, so x1, x2, x, whatever the states are of the system, you can calculate or measure them at any given time t. You can calculate or measure them at any given time t. So let us give a practical example. This is a furnace and it is operating at 3000 degrees. Any sensor you put inside here, so any sensor that you put inside here is going to melt. So you can determine the temperature. And if you can determine the temperature, which is one state of the system, maybe if I'm assuming say a furnace, so one of the states of the system that you want to know is what the temperature is. So if you don't know the temperature, then you can't control the temperature because you don't know it. You can't determine it because there's no way you can use to measure it. All right. Of course, that leads to this thing here that them have in control called state observer. So if you put the sensor out here, so and take the temperature out here, so you can calculate what you think the temperature inside the furnace is going to be. So in this case here now, the sensor would be called a state observer. So so you can use this now, the sensor over here, to estimate what is the temperature inside the furnace is going to be. But this is one system in which, like I said, if you cannot observe a state, if you cannot measure a state, so let me put measure up here because we are talking about measurement. If you cannot measure a state, then you cannot make your calculations because your output is going to be dependent on your states. This is the y is equal to something times x1 plus something times x2 plus something times x3. And if you don't know what x3 is or x2 is or x1 is, then you can't calculate your y. So sorry, this thing is not a state observer. This is a partial state observer. So observability is also key in our calculations for controlling a system. Now, mathematically, Now, if you recall, C is your output matrix. C is your output matrix. So if C is your output matrix, then what we are saying is that your output times your system, when you put them together, you're supposed to get a solution for each of the x1, x2, x3, x4, x5, and so forth that are in your system. So you can calculate the value for each state. All right. So, like I said, leaving it there when you do your masters in control in Europe. And by the way, the Center for Studying Control is not the USA, it's Europe. So let's go again. So we want to find out if this system is observable. Me a second there. Thing up here, so let's make it one whole heap of nice. No switch not available. Alright. So now, we want y, which is c and c times a, which is going to be equal to -3, -1, and then -3, -1. Somebody at the door, so come back again. Yeah. So you can see Robert as a appointment. Because Robert was saying that you there not be safe. You never know to be there. All right. So okay, so we have C times A, and our A is 0, 1, 4, 3. So we're going to boy. Maybe that is why. So I'm plugging in the computer. All right. So that's -3, -1, and 3 times 0, 1, -1 times 4. That is -4. And then 3 times 1. I mean, 3 times 1. -1 times 3. -3 times 1. -3, -1 times 3, that's -6. That's what my y is equal to. So the determinant for y is going to be equal to -3 times -6 minus -4 times -1. We know that that is 18 minus 4 equal 4, not equal to 0. So the system is observable. Means that we can know all the states at all the times. We can stick in a meter, do some calculation, and find the value for each of the states at all given times. So the thing about it is that yes, I'm working out the nice clean examples in class, but when you have the systems in real life, is a whole heap of zeros. Like I said, the last one that was kind of helping with was a 201 by 201 matrix. So before you do anything with it, you have to find out if it is observable or controllable. And yes.
Sir, the matrix on the row, sir. Oh, that was, sir. Come on, understand. Oh, you're right, it's, sir.
Oh, so this is C, which is -3, -1, and then is CA, which is -3, -1. So it's going to end up giving you a row 0, 1, 4, 3. So that's what I was taking. First one is the first row, 3 times 0, 1 times 4, -1 times 4. So that would be 3 times 0 plus -1 times 4. And that is your first row, which gives me the -4. And then the next one is 3 times 1, -1 times 3. So the next row is 3, -3 times 1 plus -1 times 3. So the first one in red give me the first, the -4, and the one in blue give me the -6. Yeah. But you never fret up yourself too much about the multiplying of the matrix, because let us see how far I got, so that I can declare independence from the CC one. Nope, can't declare independence. So bigger matrix. Alright, so we want to determine if that matrix is observable. Alright, so I'm hand back over in MATLAB. So now our matrix A is 0, 0, 0, 1, 0, 0. 0, 0, 1, 0. 0, 0, 0, 1. -4, -6, -2, -1. B is equal to 0, 0, 0, 1. have to put a bracket. Apostrophe. And C is equal to 1 -5 -2 -4 that's our C. And then our Y now, Y equal C
What that go, sir?
C, Y equal square bracket C. Then the next one is C times A. Then the next one is C squared times A. 4 of them we must have. And next one is C cubed times A. Close bracket. Apostrophe for the transpose. Oh, sorry, wrong. So put what is C times A squared and C times A cubed. Oh, next thing. put in put it back and put in a semicolon in between each of the terms. Okay. And then you can type in rank Y or determinant of Y, whichever one. The rank of Y is 4. Determinant of Y not equal to 0. Then it is.
Just wait. One, PJ.
All right. So now the two things that you have to determine before you launch off onto any of the things that we have been talking about is that you have to you have to determine whether they're observable and controllable. Because if they're not controllable, you can't find an input, and if they're not observable, you cannot find a state. Yeah, or one or two of the states cannot be determined. All right, now observable, OLOX, SRSV. Type in OBSV. Teacher should just type in wait. Give him back. OBS. Just type in OBS. And then type in A bracket A and C and see if okay. So it asks me, right, is that the same matrix? This one is transpose. Right, one is a transpose of the other. It doesn't really matter because whether the transpose or the right way, you still can determine. So it's OBSV. I was correct the first time. All people can remember the command in them head here. All right. So now you can get the observability matrix, and then what you do is that you would find the determinant or the rank of the observability matrix, and then that would tell you whether the system is observable or not. All right. So here we go back now and look at our problem, and then discuss how it is that we would do the problem.
Sir, can you go back up to the question 1 second?
This question here are the one that we work out.
That one, sir, I got it. Thanks.
All right. All right, so we can attempt this problem here now.
Yes, sir.
Me say yes or no.
Yes, sir.
Okay. So the first thing we have to do is go through the same thing that we talked about last week. I just checking. Something here. Okay. So so um so once again we have to find damping ratio. So that is how much that work out to? ln squared 0.1 over pi squared plus ln squared 0.1. How much that work out to? I think we worked it out already. Yeah, how much you get for this?
0.09.
0 point?
No, it's wrong answers.
What you get? But what did you get? I don't have a calculator with me, so what you can use. nobody now talk to me, so we get 0.349. That is what we're working with. Are you still there?
Yes, sir, we're still here. A bit distracted. Yes, sir, we're still here. A bit distracted.
Oh, okay. So all 22 are still distracted. Sorry, all 21. All right, certainly.
Alright, now 0.591.
Right.
Yeah, man. No, we get a volley the 2 time already.
Yeah, exactly. All right. What's the formula for cycling time?
We got 4 over whatever, something there again. Damping frequency omega n.
So it implies that omega n is equal to 4 over
Damping frequency times cycling
times
time.
cycling time. 4 over 0.591 times
35.
what we said the cycling time was again
5 seconds.
5 seconds.
One point 35.
0.35.
1.35.
So our GS, which is equal to omega n over s squared plus 2 damping ratio omega n s plus omega n squared is going to be equal to 1.35 over s squared plus 2 times 0.591 times omega n, which is 1.35 s plus 1.35 squared that's 2 times 0.591. 1.35.
1.59.
Got it, 1.6.
Point 82.
Alright, so 1.82. Alright. So he's way doing that because we're going on MATLAB after this. So our equation is 0, 1, 0, 0, 0, 1, negative 2, negative 3, negative 5, 0, 0, 1, and this is 0, 2, 1. Alright, so So write down this equation for GS. And then we go into MATLAB. Alright, so Sir Campbell,
Yes, sir.
we're going to MATLAB now. Alright, so we're going to, our transfer function is 1.35 divided by s squared plus 1.6 plus 1.82. So first thing we want to do is find the roots of the denominator. So we're going to type in x is equal to the 1 square bracket, we put this on vector, right? 1.6, 1.82. Put in the 1.6.
What that, sir?
1.6, 1.82.
Oh, sorry. 6.82.
Alright, close the bracket. And then we're going to set the roots of x. So we want to solve that equation for the roots of x. Alright, so the roots of x, let me see, that is 0.8. 0.8. Alright, so remember now, it's a 3 by 3 situation we have. So the new root that we're going to put in, the desired roots are 0.8, negative 0.8, negative 0.8. So we're going to put in another root. So the root that we're going to put in is going to be 10 times more than that. So it's going to be negative 8. So here's what I'm going to ask you to write down. Now, when we're doing this thing in MATLAB, we are going to write down the 3 roots. So we're going to write down K, capital K, is equal to the square bracket. So we're going to put in negative 8 and the other 2 roots that are there.
So that is negative 8, and then you have negative 0.8 plus 1.08. I can put in the I just like how it is there.
Yeah.
Right. Minus. Should I just copy this in?
Sir, where did it come from?
Where did 8 come from?
Yes, sir.
Alright. Remember now, it's a 3 by 3 matrix we had. So we're going to put it's a second order system we just work out. So the 2 roots of the system are negative 0.8 plus or minus 1.0863i. So we have to put in a new pole in the system that does not affect anything. So that's why we said the new pole has to be at least 10 times the real part of the poles of the system that we, so that those two poles will be dominant and the other pole that we added is not
Oh.
dominant. So I just multiply the 0.8 by negative 0.8 by 10 and get 8. So I'm putting
Oh.
that as the new pole.
Okay, sir.
All right. So that is our the K represents the poles of the system that we now want. This is the design. So you can put a comment inside there. Say, or you put comment in the MATLAB again. For that, or we're gonna put the thing there. Percentage side.
You know, so I guess me not remember. You know, I think
I think a
God is-
percentage.
Oh, it's percentage. Yes. Right.
All right. So desired poles of the new system. All right. So now, so this is the desired poles of the new system. So we're going to type in now the old system now. So we're going to type in the A. So A was 0, 1, 0. Zero, 0, 1. Negative 2, negative 3, negative 5. Put in the space them.
Yep. Yeah, man, them in there.
0, 1, 0. All right. And then we put in our B. Zero, 0, 1 transpose. From our outside. And put in our C. Which is 0, 2, 1. All right. Now, you're going to type in. So now, when we're using pole placement by this method, what we are going to say is place. What variable are we going to use? Z. Z equal place. And that Z we use it. I shouldn't have called the thing up here K. I should have called them P for poles. But alright, that's alright. So call Z equal place, open bracket, A, see the example there, A comma B comma, we use K, capital K, yeah. So that those values that you get there now are the gains for the system that you would need to work out. Alright? So that will be the method by which you work out the gains for the system that you get. The required gains. So that I should have called, what I call K should have been P for poles of the system. And what I call it Z should have been K, just to represent gain, because we usually use K, K1, K2, and K3 for gain. But here is the thing that we are going to work on another problem now, and we're going to work it out exactly as how we are required to work it out. So, so let's go back to the drawing board. It's another problem. Alright, so as you can see, it's the same. We're going to end up with the same characteristic equation. But so let us go back through. As a matter of fact, let me change something so that I don't want us to miss anything in the calculation. Yeah, alright, because we're going through the full calculation. So, okay. So in this one, we know that the damping ratio is 0.591. And then now we have omega n is equal to 4 over the damping ratio times the cycling time is 4 over 0.591